Welcome to part 2 of section 1. So, continuing off of what we covered in part 1, we will continue to look at sets, and now we will look at set operations. Sets can have operations just like numbers do. Just like numbers may have addition, subtraction, multiplication, division, and etc. But those are some operations you might see with numbers. So, such operations for sets include union, and a union is a combination of sets. Notation is a U-shaped symbol. So, an example. For sets A and B, A union B is equal to the set of X, where X is an element of A, or X is an element of B. We also have intersection. Let me try to make these notes a little more clearer. I'll try to slide this over where it looks like. It's like that T didn't want to move over. Let me correct this real quick. There we go. Make these notes a little bit more clear. So intersection is a set with elements that are found in both sets. Notation is an upside down U-shaped symbol. An example. For two sets, A and B, A intersection B is the set of X, where X is an element of A and X is an element of B. And the reason you may notice that I've underlined, the words and or for union and intersection. And the reason being is that, try to fix that, there we go, is that the word or is used for union because we have both elements of A and B, and then we have the word and for intersection because we have elements that are contained both in A and B. And sorry, I said that wrong. The or means that the element is either in A or that it's in B for union. Because for intersection, we're focusing on just the elements that are in both sets. All right, another operation is difference. And that is a set where all the elements are unique to a set. The notation will be a subtraction symbol, or in some writing they may use a little slash symbol. So an example for two sets A and B the difference of A and B is a set of X where X is an element of A and X is not an element of B. Let me try to rewrite that. So we also have a complement. It's another operation. So when looking at a universal set, a complement represents the elements that are not part of a set. So the notation will be a line over some element, or you may see a superscript of C. So an example. For a universal set U and a set A is equal to U minus A, which is equal to X, the set of X, where X is an element of the universal set, and X is not an element of A. So that is all the most common operations that you'll see. So these operations can be described using Venn diagrams. So, for example, say that this entire rectangle or square represents the universal set, and we have these two Venn diagrams that represent sets A and B. If we shade in, which represents the set that we are looking at, we shade in both sets A and B, we have A union B. Here's a Venn diagram representing A union B. I just want to share a fun little note for union. So the way I've always been able to remember union is that union starts with U, because the symbol that represents union is in the shape of a U. So this is a easy and fun saying that personally for me has helped me be able to tell the difference between union and intersection. Union starts with U. And going back to the Venn diagrams, we'll look at another one. We just say this region right here where both A and B interact with each other. This is A intersection B. And we'll try to copy this so we won't have to draw it again. Make another one because there's two more Venn diagrams that we'll look at. So if we just shade in the Venn diagram for A, this is the difference of A and B. Then if we just have a set A, then everything in the universal set outside A is shaded in, but A is not. This is the complement of A. Another note about set operations is sets are said to be disjoint if they have no elements in common. So, for example, if you have two sets, A and B, the intersection of A and B would just be the empty set. Often more than two sets will be involved in operations. Just for example, we have three sets, A, B, and C. Well, if we were to draw a Venn diagram representing something like this, we have a universal set. Then inside the universal set, we will have three sets represented by these Venn diagrams, A, B, and C. So, the union of A, B, and C be equal to the set of X, where X is an element of A, or X is an element of B, or X is an element of C, and so on and so forth. The setup for the other operations of sets are similar. So other operations are similarly set up. With just another set to be considered. So, for sets n is greater than 2, where n represents the number of sets a more convenient method of writing can be used. So let's say A sets A1 union A2 union so on and so forth, all up to sets of A n can be written as the union of I equals 1 to n of AI. So, another description of this is the set of X, where X is an element of AI for some I where 1 is less than I, less than or equal to I. Put that in the wrong place. I is less than or equal to n. And similarly, for intersection of multiple sets, the intersection from I equals 1 to n of AI is equal to the set of X, where X is an element of AI for every I where 1 is less than I, which is less than n. However, sometimes sets cannot be conveniently described as above. When this happens, we can introduce a non-empty set. We'll call it I, called an index set. And this will be described using an italic I to help not confuse it with I for irrational numbers. So, for a set, let's call it S of alpha, for each alpha that is an element of an index set, the set of S alpha in relation to alpha element of the index set describes a collection of all sets S alpha where alpha is an element of an indexed set. This is called an indexed collection of sets. So, some operations for these collection of index sets. Say we have the union, where alpha is an element of an index set of S alpha. It's equal to a set of X, where X is an element of S alpha for some alpha element of an index set. And also intersection of alpha element of an index set of S alpha is equal to set of X, where X is an element of S alpha for all alpha is an element of the indexed set. Okay, so that is it for set operations. Now we will change topics and we will begin to look, we'll change colors here. We'll begin to look at partition of sets. So, recall, going back to set operations, that two sets A intersect B is an empty set. If it's an empty set, it's called disjoint. So a collection of subsets S, and this is a different form of S, where we just have a little line coming off of both ends of S to help differentiate between other uses of S that we may use. A subset S of A is called a pairwise disjoint if every two distinct subsets of S are disjoint. So a partition is a collection of pairwise disjoint non-empty elements of a set. Excuse me, sorry. This is subsets. There we go. So, just a sub note. Additionally, every element of a set must belong to a subset. So here are some properties of a partition. Where S represents the set of the subsets. So the first property is X cannot be equal to the empty set for every set X that's an element of the set S. Second property is for every two sets X, Y as an element of the set S, either X must be equal to Y or X intersection Y must be equal to the empty set. The third property is the union of X is element of S of X must equal A, where A is a set. So here is an example that we will look at. Say we have the set A with elements 4, 8, 12, 16, and then we have the set S1, and these are its elements. We also have this set S2 with these elements. And then we have the set S3 with these elements. So, if we were to look at these three sets of S and determine if they are a partition of set A, set S1 is a partition we have all the elements of A inside all of the subsets or elements of the set S, so we are good. For set S2, important thing to look at is that we have a repeating element of 8, so set S2 is not a partition of A. Let me correct my wording up here, of A. Because we cannot have repeating elements. And then there are two important things to look at for set S3. First, we have the empty set as an element, and also 16 is missing. So set S3 is not a partition of A. So now let's look at a fun little picture here to describe partitions of a set. So imagine a partition as a pie. So we'll draw out a pie here. We'll get a little colorful with our colors here. Let's start with doing, see if I can get brown on here. That should be close enough. So we'll just draw a big circle. Then we'll try to color it in here. Let me change the thickness of the pen. And we'll just draw a little pie tin crust, or a little pie holder, and color that in too. We'll get a black line on here. Put some little edges on the pie. So, if we are let me get my color back here. So, for the subset S1, if we were to represent this as a pie, if we go back up to S1, we see that there are 3 elements inside S1, where one is a subset of A with the elements 12 and 16. So let's get this pen color back, and we will draw, let's try to split this into 3 sections because we have 3 elements. So we have 4, 8, and let's put 12 and 16 in here. Just wanting to color this in some more, so put some little steam coming up, like it's a fresh out of the oven pie that you can smell. But this is a fun image to give you a visualization part of partitions. Just draw a little smiley face person here. Give this image some character. He's ready to eat is partition pi. Yep. All right. We'll look at one more topic for this second part of section 1. And let me change colors here. And the last topic we will look at is Cartesian Products. So, recall, if a set A has two elements, x, y, then A can be represented as a set of x, y. I drew that bracket wrong. Or the set of y, x. An important thing to note here is that the set of x and y is not equal to x and y in parentheses. And I'm going to pull out a highlighter here because I believe this is an important thing to realize and understand. X and y in parentheses is an ordered pair. And an ordered pair is a single element that contains a pair of elements. So, a Cartesian product of two sets consist of all ordered pairs where the first coordinate belongs to the first set and the second coordinate belongs to the second. So the notation is x, or not x, sorry, the multiplication symbol. So an example will be for two sets A and B, A is equal to the set of the ordered pair A and B, where A is an element of A and B is an element of B. Another example. Let A be the set of 1 and 2, and B be the set of X, Y, and Z. So the Cartesian product of A and B is 1x, 1y, 1z, 2x, 2y, 2z. So basically imagine like back in algebra you may have learned about foiling. So imagine you're looking at set A and you're distributing 1 to all the elements of B and making ordered pairs, and the same goes for 2. The last note to make here is for cardinality of Cartesian products. So for two sets A and B, the cardinality of the Cartesian product of A and B is equal to the cardinality of A times the cardinality of B. So for the previous example, the Cartesian product of A cross B, we go back up. A has a cardinality of 2 and B has a cardinality of 3. So it's equal to 2 times 3. So the cardinality of the Cartesian product of A and B would be 6. And if we scroll back up to the Cartesian product that we found earlier, we can count 1, 2, 3, 4, 5, 6 elements. Okay, so that is it for section 1. Thank you guys so much for watching, and hope these lecture notes have been helpful to you. The next video will be about some examples from section 1, and then section 1 will be finished for these mathematical proof lectures. So, thank y'all.